Well, hi, good morning. Thank you for joining me in my shop here. It's Wednesday, May 4th today, and we're looking at a radio that's largely working. In fact, it could be performing really well, in fact. But there are a few other interesting things that are worth checking out and poking around with. But I'm not sure about raising the performance of this radio much beyond where it is now. So one of the things that caught my attention is the fact that there's a glass tube here, but all the rest of the tubes are metal, except for the rectifier and the output tube. Why the glass tube here? This is a 12 SA7. Why the glass tube? So I took a look on the schematic. I won't show it to you right now, but it identifies two 12 SQ7s as being glass tubes. Those would be these two, but they're metal. Now this one is just calls a 12 SA7, doesn't say GT after it. There probably would be better if there's a metal tube here than the one that's there. How much better? Can we even find out? Can we even figure it out? So that's one interesting thing. Another interesting thing, or curious thing, maybe curious is a better word, is what was going on back here at the earphones, or the phones, headphones, or whatever you want to call it. And this green wire, I don't know if you can kind of see it there right where my finger is. There's a green wire. It's coming from this pin over here. It just runs along, and then it's wrapped rather carelessly on another wire here. Now I've got enough experience to know that sometimes those things are actually intentional in the design of the radio, and they're commonly referred to as gimmicks. So there is a gimmick appearing on the schematic. I just saw it. So I think it might be interesting to look into that also and just see, is this the gimmick? Or is it somewhere else in here? I haven't spotted it yet. Why don't we start off with that? I'm not quite sure how to deal with the glass tube, because I want to know if it makes a difference when I change it. So to think about that one a little bit, but we can look for the gimmick in here. Let's start with the schematic. In fact, it might even be worth, why don't we run through the entire schematic? That sounds like fun. Okay, so here's the schematic. Right here's the whole thing. Let's just start with all these notes and read the notes. Voltages at tube terminals. We can expand this a little bit. Voltages at tube terminals. All voltages are DC unless otherwise specified. Oh, so here's it. Hey, I didn't notice this until just now. Chart of the pin voltages. That's real helpful. Voltages were taken with an electronic voltmeter. So a vacuum tube voltmeter probably. No signal being received. Control set as follows. Note, resistance values are in ohms. Mica capacitor values are in picofarad. Paper capacitor values are in decimal equivalents of microfarads. So I think what that means is they're simply writing the number here. Like if we pick one, here's one, 0.02. And you don't bother putting gallon case, no problem. Electrolytic, got it figured out. Did you follow that? Electrolytic capacitor values are microfarads. Denotes electrical shield. Denotes unshielded unit assembly. Denotes mechanical ganging. Letters at band switch 1 and numerals at antenna and oscillator transformers identify corresponding terminal lugs on pictorial views. So here's the pictorial views with all these numbers written on it. Okay, what's across the bottom here? Frequency 455 kilohertz on the IF. 7 kilohertz wide at 6 decibels down. 65 wide at 60 decibels down. It's pretty hard to hear any of that. Gives an idea of the shape of the response curve. Image ratio. Now this is of interest to me. I actually wrote the ratio in here. 2.7 to 1 at 30 megacycles. 6 to 1 at 14. 10 to 1 at 5. So what they're saying here is if you tune in a signal and then arrange a signal at the image frequency, that signal at the image frequency will be, in this case, better turn it the other way around. I guess this must be the image. The signal at the correct location will be 2.7 times stronger than the image. Here it's 6 times stronger, 10 times stronger, 35 times stronger. So it's 35 times stronger on this band. This is the broadcast band, because of the way images are, how can I say it? The broadcast band covers a wide range of frequencies, believe it or not. You might not think of it that way, but it does. Because it starts at 500 and ends at 3 times that frequency, 1500. So that's a huge decadal range. I don't know how to describe it. That's why the broadcast band is so impervious to the problem of picking up images. But when you get up on the top band, and this radio goes up to 30 megahertz, that starts becoming a much bigger problem. That you can pick up the image almost as strong as a regular station. And you know, I had another Hallicrafters radio in here, very similar to this one. I think a simpler version of it, maybe a later version. I can't remember if it was the E or what. And it had a terrible time with images. Well, it's actually not a terrible time, because it seems like you're picking up an awful lot of stuff when half of it is image signals. So so if you're listening to a strong station, and then you started tuning your radio up a little bit, and you picked up an image, and the image was, in this ratio, weaker, about a third the strength. You just think it's another station, just a weaker station. You wouldn't think it's an image. I wouldn't. It's a much bigger problem than might be said, and that includes things like noise and other stuff at the image frequency. It doesn't have to be a station. Okay, they give sensitivity information here for a 50 milliwatt standard output. Might be interesting to try this. This might be helpful with the changing of the 12 SA7 tube and trying to determine if it was a good thing or not. Audio output. Okay, good for that. Dimensions and proportions are shown in pictorial views have been exaggerated for clarity of terminal lug location. Very seldom do I have to deal with coils like this in these old radios. Very seldom is there an actual problem with them. And there's the layout of the rotating switch. Okay, now I'll run through the schematic here. Well, isn't this entirely different already? It's entirely different already. In my radio, there are capacitors here on each one of these legs. Not just this one. Makes me wonder if I've got really the correct, well, it's got the right name on it, the correct schematic. Here's the 12SA7 I was concerned about. Pin 1 is the suppressor, and it's just grounded to the chassis. What are they doing with the cathode? So the cathode has the oscillator coils in it, the cathode circuit, and the oscillator this first grid number 1 is the oscillator grid. So, okay, we have a screen, and then we have the signal input coming from whichever of these coils is selected. What's that guy right there? Resistor. So the switch and the switch, they work in tandem. The unused coils are grounded out. The higher coils, lower coils, because as you swing this along, why do they show Q way over here? P-O-N-M. It's a 4-position switch. Over here. Okay, don't quite know what's going on with that. Probably won't matter at any point. We've got a capacitor paralleling a resistor going to the chassis. Okay. Not too much to say about any of that. So after the mixer tube, we go into the IF. All looks pretty standard. This is the capacitor I changed already. This is the switch that puts the radio into standby. It just basically interrupts this tube. And down here we have the beat frequency oscillator. So this is an oscillator running here. I think it's running near the IF frequency, I think. And then it's injected, so to speak, right up into this grid. So if you have this on and oscillating, you're going to put an additional oscillation in here. Basically, you're replacing the carrier that's missing in single sideband transmission. You're supplying the carrier from here. It also has the one diode being used here as the noise limiter. Probably why they picked a SQ7 tube, because it has the diode available. Because both these diodes are being used here in this detector. Okay, jumping ahead a bit. So we're going through the IF amplifier, coming out. Audio is heading this way to the volume control. That's indicating a shielded cable. 10 megohms. You're up to the grid. Oh, I missed that ground symbol right in the middle here. We are picking off some of the audio through a small capacitor and on its way. Okay. Now, also coming out of the detector is the DC result from rectifying the IF signal. The DC result is sent this away. There's no real current flow in this circuit because all it does is go to grids. It takes a long route here. One of those can markings, I just barely see it. These coils are canned up in some way. This one isn't. So how are we getting there? How's this? Well, I don't see. What's this dot doing here? Why is there a dot in the middle of the line? Well, maybe the AVC is not applied when this band is operating. Which band is this? Band D. I assume this is the band number? Maybe not. No, the bands in this thing are numbered 1, 2, 3, and 4. Well, don't quite see it. But you can guess this is, we can guess this is the broadcast band here. Okay, and then otherwise the signal, the AVC will get through this way. Okay. Okay, out from the IF. Audio comes down, it's fed back around to this grid. Over here, we already checked this capacitor, found it changed by someone else. We replaced this bypass capacitor. We checked the bias here, -7. It's supposed to be, it's coming up -6.5, something like that. Okay, not too complicated. Nothing too complicated here. The output then goes through the output transformer and on to the speakers. Unnecessarily complicated looking deal here. Is there a ground applied anywhere out here? No. So just by virtue of this transformer, the speaker wires, headphone wires, all that are isolated away from the actual radio. So the problem with the hot chassis is not is not here. Is not meaningful with the speaker and the like. That's good to know. Good to know when I'm doing testing. That's it. That's the end of the run through here. Very good. So gimmick. I went to this whole thing and never saw the gimmick again. It's a capacitor that says right there, twisted leads. We gotta find this. So it's coming off of pin 2 of the oscillator, the BFO. Pin 2 of the BFO. Okay, now where is that tube located? There's two 12 SQ7s. Oh, I could probably figure it out because of this control. This is a control that's on the front panel to vary the frequency of the oscillator a bit. Okay, let's look back at the radio. We'll try to find these twisted leads. Okay, so the two two 12 SQ7s are this one and the one beside it over there. That's these two. But you know what? The green wire's coming off of this one. Now one of them's going to be connected up to this. This is the adjustment from the front panel for tuning the BFO. And it comes along the shielded cable here. And it arrives at this tube. So then there's a green wire coming off pin number 2. Was it pin number 2? I gotta peek again. I forgot already. Let me just peek at it here. I think it was pin 2, wasn't it? So twisted leads, pin 2, coming off pin 2. So this green wire is a capacitor. Is effectively a capacitor in here. Right. This one appears to just go nowhere. Boy, good thing I didn't unwrap it and solder it there. That was my first thought. Okay, that's a pretty clumsy looking job done there. But that's okay. We'll leave all that alone. It's all related to the BFO. Still don't know really how this was wired up and what happened here. Something happened here. Uh-oh. Time to deal with something else. Well, one thing led to another, and it's the next day. 24 hours has gone by. That distraction took me away. I never made it back into my shop again. So, okay. What we were looking at was the little green wire here, and I think we pretty much did with that. The thing I'd like to focus on now is the deal with this chassis and that cabinet, and the way things are grounded. I hate to use that word, but I'm going to use that term. How the cabinet is connected to the chassis, or is it? So one of the things I noticed early on is that this is a hot chassis radio. This is an example of the worst type, where there is a direct connection between the power plug, one side of the power plug, and the chassis. With an unpolarized power plug, then you never know if the chassis is plugged into the hot side or not. And the other thing about those radios, or this type of radio with an unpolarized plug, is regardless of which way you plug it into the wall, if it's safe when it's on, it's unsafe when it's off, and vice versa. There's no way to escape the unsafeness of it. So a typical way that these things are dealt with is the unsafe metal, the chassis here, is kept out of contact from the operator. The operator cannot touch it. I think I was talking about the plastic knobs and a few other things. So how are they doing this? Because that's a metal cabinet, and for crying out loud, if this is in contact with this, then touching this is very dangerous. Now I put a polarized cord on here. It makes the radio a lot safer, not 100%. I also noticed that all these terminals at the back, each one of them is protected with a capacitor. And what's really being protected is the person out here who could touch these, including even the ground terminal is connected to a capacitor. That capacitor, actually this is the one, this is the capacitor is going to a terminal that's tied right to the metal chassis here. So another couple things I've noticed along the way, which I think are part of the puzzle, are these two panels here, which are loose. It's kind of weird that there'd be something bolted to the chassis but still loose at the same time. If we start taking a look at this, some of the mystery is going to start disappearing. So what is this? This brown piece. Look, there's paper here, stiff paper here. What is going on here? So there's a rivet, I can feel it with my finger, right into this metal bracket. That rivet must be coming up into this brown piece. This must be a method for making sure the metal rivet is not touching the chassis. There must be a sleeve in there or something going on to achieve that. So there's no connection between here and this chassis. Now, just to prove that a little bit, nothing. Bad contacts here. Let's try this. That's interesting. Okay, another interesting thing which I'm observing for the first time, but it's been staring me in the face, is how these are handled. Again, more paper and a rubber piece here, and the screw that's going down through here. What is going down through there? Back of the radio. Right. What the significance of this, but under this panel, screws. If I remember right, do I remember right? those two screws. Which are actually a nut and a screw. Come up through here. That's an insulated material inside there. That brownish color you can kind of see. So, oh my gosh, they've actually managed to have a big metal chassis inside a big metal case and isolate away the chassis from the case. And here is the key capacitor here. It's connecting the case here. I'm sorry, the chassis, I better use the word chassis here, to this piece. And then this piece is screwed onto the case, and that's the capacitor that has the, in the schematic, that has the different symbol. So we should really make sure this capacitor is good. In fact, it's probably worth changing this one. We'll give it a quick test here. This is not a very valid way to test a capacitor. Just reading the resistance on the meter, just going up, up, up. This is a 60 megohm meter. We read 60 megohms. Okay, this is stalling out around, probably going to stall out around 50 megohms. Pretty hard to get a shock through a 50 megohm leak. I'm not going to worry about this right now. So another capacitor of interest would be, when I get around to changing some capacitors, I'll change that one too. Another capacitor of interest is the probably a 0.05 capacitor on the AVC circuit. And we should take a look at where that might be. Let's take a look on the schematic here. Okay, so we're looking for the AVC capacitor. It's going to be on the far side of this big resistor here, 2.2 megohm resistor. And here we are, 2.2 megohm resistor, and there it is. This guy, we got to find this guy, C16, and change him. 0.02. If there was a capacitor with a leak in it that might cause a problem, this would be one. Because this is hooked up to a very high impedance circuit here, so a little bit of leakage out of here could have a significant bearing on the charge that remains in this wire. So where's this guy going to be? Well, maybe if we can find this, we might be able to find that. I don't know. Let's go looking. Okay, so which one of these capacitors is the one in question? It's not going to be these. It's not going to be this. This one is a 0.05. We're looking for a 0.02. That's a 005. That's an 01, 0.01. That's a 0.05. This one, I cannot see the size of it. This one here. So by elimination it would have to be this one, but that's not very certain. So the next approach is we find that unusually large resistor, unusual in the sense that there's probably only one resistor of this kind of size in the radio. So we're looking for a red, red, green. Red, red, green. I see a red, red, black. I see a red, red, yellow. I see a red, red, green right here. So we'll assume that this is the AVC resistor. I'll call it that, the AVC resistor. On one side of it is this capacitor I'm hunting for, and on the other side is other stuff. So if we go on this side and we look, we see a resistor, and there's a wire inside a shield. Just doesn't have. That's not adding up. That's more likely the audio going out. So if we get on the other side of this resistor, okay, we see a brown wire brown wire heads way over to this switch here. No capacitor there. So we follow this wire, disappears into one of the IF cans. As we follow this brown wire here, it comes up onto this bracket. I might just take a look at the technique they used in building this radio. So they have a large coil form here with 1, 2, 3, 4 windings on it. They have something very similar over here, large core, windings on it. And then they have a mounting bracket, this piece here, you can see it here. And then they've mounted these guys, these capacitors, up on it. Basically, you couldn't get them any closer to the coils they're related to. It's really a very efficient design. Saves a lot of space in the radio, saves a lot of problems with the mounting of these guys. It's really quite clever. So there's a heavy bracket through here, and we see the brown wire comes up to the bracket. The bracket is a continuous piece of metal all the way to here, and we see that capacitor connected right here. So that's two fingers pointing at this capacitor now as being the one in question. And the last thing is, one side of this capacitor should be grounded. Let's find out. It would not be this side, it would be the other side. How can I get down there? There it is. That's got to be the capacitor. That one I think is well worth changing. So that's two. This one and that one. Okay, I'm going to change those two capacitors and then we're going to test the radio. Okay, so I've changed both of those capacitors. We're going to find out now, does the radio still work? Before we do that, let's find out the condition of those two capacitors. That sounds like fun. There they are, waiting right there. This is the one that was going to the case grounding capacitor, if you like. It says 0.025 on it, but on the schematic it says 0.25. So obviously this is some kind of special capacitor here. Okay, let's check it out. Now this one, if it were really leaky, might be involved with giving you a shock off that radio. So it would be important to make sure there's not a leaky capacitor in that position. That's why I've changed this one out. Okay, all set here. Watching the eye. What's it do? Opens up. 150. Can't do it. Just can't do it. So leaky to some degree. Unfortunately, I can't relate this test to, is that a shock hazard of some sort? Obviously, it would leak a little more current than if it weren't leaky, but there's a current flow through the capacitive side of it too. That's probably much greater, in fact, than the leak current. Okay, 50 volts. This is the AVC. I never looked to see if it's a 0.02. I just want to, yeah, 0.02. Good. That's good. 0.02. 50 volts. What do you say? Right open. See that? Right open at 150. Wow. Okay, so this was a pretty good capacitor, in fact. During its life, it's normally not doing much, right? It's only got 10-15 volts across it at most. Not a lot. Okay, so we probably could have gone along without that, and another way to put it is probably didn't make much difference changing the AVC capacitor, but it's done now. Okay, we're ready to go here. I have an antenna connected, speakers are connected, switch is on, Dim bulbs behaving normally. It's a beautiful day here today. This is the first really beautiful day. It's going to be 16, sunny all day. So that's where I want to get to. I have the antenna switched on and the antenna is connected. Ground wire is not connected. We're on band 1, which is the broadcast. This takes a long time to warm up. Wow. So hear the tone. Seems to be a tone with every station, every signal. I mean, it's hard to tell. There's so much noise and weird signals in the signals, but I think there's a heterodyne in this radio too. Which we won't worry about just yet. Okay, and didn't seem to perform quite as well. I seem to remember this picking up some AM stations. Okay, we're going to go up to the top shortwave band. (15, 16 megahertz). In this area we should pick something up, especially 15707 right up around here, I imagine. No? I'm looking for 15770 is what I'm doing. That's probably it there. Getting noisier. Okay, not much happening there. We'll go to the next band down. This is 5 megahertz up to 14 megahertz, so this is a pretty important band. 6, 7. 9.
Lo que tienen que decir los otros versículos bíblicos relacionados con el mismo tema. Y ya se puede comprobar casi cualquier cosa de esta forma. El mayor problema es intentar establecer una doctrina de esta.
Okay. And we did all that with the voltage restricted a bit. 107 volts on the radio, not 117. Okay, though. Certainly is a hum coming from this radio too. Okay, so we didn't kill it. Changed a couple more capacitors. Don't think it made too much difference in the operation of the radio. If anything, it seemed to go downhill, but I think that's just an imaginary thing. For instance, I didn't have the ground. Hey, I didn't have the ground. Hey, let's just turn this back on quickly. I didn't have the ground on here. Let me attach a ground. We'll go back to AM. Down around here. Okay, I'll attach the ground. Turn it up. Still not picking up. I'm going to try one more thing here. Okay, switch to another antenna. So they're both very similar antennas.
Les mariages gays, par exemple, les enfants issus des mariages gays, le droit de la famille, pour ne mentionner que ces sujets, et attendez-vous à des positions de plus en plus radicalement de droite de la part.
Okay, I'm off. I'm going to switch the antennas and just see if this station disappears as another experiment here. Okay, this is the other antenna. Just barely hear it. Very good. Okay, that's the end of the experiment. So I'm always curious about I have two antennas and I'm always curious about which one's working better. And they vary over the frequency band. They're crazy. Crazy antennas. There we go. Very good. Radio's still working. Thanks a lot for watching this video. What I'm going to do next with this radio, I'm not sure. I'll think of something interesting.